Okay, hi everyone. So our second keynote. We are honored to have Sabine Süsstrunk as our keynote speaker. She's a professor at École Polytechnique Fédérale de Lausanne, EPFL. Her talk will be last for 25 minutes, and after that we will have 5 minutes for questions. So the QR code to submit your questions you can see in the live stream and in auditorium on Getatown. So Sabine, stage is yours.
Well, thank you very much for the introduction. And of course, also thank you very much to the organizers for the invitation. So in my talk about visual computing, facts, fakes, and fiction, I'm going to take a little bit more of a bird's view than the two presentations you've already seen. And of course, because the talk is 25 minutes, I'm not going to be able to cover everything. So be aware and be prepared for a very biased talk that also takes somewhat of an academic position versus maybe an industrial one. So just to introduce myself very quickly, as was said, I'm a professor at EPFL in the Computer and Communication Science School on the lake of gorgeous Lake Geneva, or the shore of gorgeous Lake Geneva, where I lead the Images and Visual Representation Lab, IVRL. Our imaging research is actually at the intersection of algorithms, including machine learning nowadays, of course, human vision, modeling, and physics, with the goal of improving photography. Just not medical imaging, not robotics, not anything, but just photography. Our application domains are thus computational photography, computer vision, image quality, and image aesthetics. So why photography? Well, it is actually probably still the majority of images taken if one considers the trillion of images that are nowadays taken by the smartphones. Second, it's actually a relatively difficult task because image quality with photography is in the eye of the beholder. It's actually, we look at photographs and judge them well. But it's not just actually in the eye, it is actually in the brain of the beholder, because until we perceive an image, there's a lot of nonlinear processing going on. So there's no direct objective measure of what we perceive as being good to the physical signal we capture. And that's still a challenge that is going on until today. And third, well, I just always loved photography. So I basically started out, and here you can see in the gray hair, with physical chemistry on my bachelor, because photography at that point was still in film, to then afterwards signal and image processing in the early days of digital photography, to nowadays, of course, also computer science in general and computer machine learning in specific. So let's start off with the facts. So it's absolutely a fact, and I think you'll all agree with me, that deep learning using convolutional neural networks on GPU has moved visual computing, and here, if you will, you can say special computer vision, from a mostly academic discipline to an integral part of a large number of discipline and activities. And this is also why we have this conference, right? So data science, machine learning is everywhere. And it's probably nothing that illustrates this better than the attendance at the premier computer vision conference. That is actually CVPR, the Computer Vision and Pattern Recognition Conference. So first held in 1983, quite a while ago, we also had about 1,000 attendants, right? In the beginning, even less, and a few papers. But as you can see here, this is a graph that actually only starts in 2006. In the last few years, the attendance has just absolutely exploded. I don't have the numbers for 2020, but 2020 was a virtual conference, so it probably wasn't that representative. But even 2019, as you can see, the numbers have increased by a factor of 10 over the last 10 years. Keep in mind, there are not many more PhD students in the domain, some, and there's not many more professors in the domain, some, but it's mostly due to the attendance of technology companies and of users of that technology. But it's not just represented in the attendance, it's also actually representative in the authors of paper at this conference. So this is now numbers from ECCV, which is also one of the top computer vision conferences. And if you look very quickly, you see that Google, Facebook, Microsoft, and Huawei are on the top of the authors per institution of accepted papers at these conferences. The next big block of authors come from China. So what's my point? Well, my point is that visual computing is very much now moving towards industry. And the reason for it is they have data that's not available for academics, and they have computing power that is not available to academics. And I'll get back to that in a minute. Now, of course, the predominance of the Chinese universities is just because they are very good, quite frankly. They develop their own systems. They are basically independent of most of the Western system that we are using, that is developed by Google, Facebook, Microsoft, and they are just one big country. So let me come back to what actually happened in the last 10 years. Well, what happened is, and you all know that, is basically the development of neural networks. And let me illustrate this example of image classification. These are image classification results on ImageNet. I'll come back to ImageNet in a minute. It's a very large database. So basically, ImageNet was basically built in 2009. And in 2010, oh, okay, let me actually say that before. ImageNet is a large database of labeled images that basically have a label of what is in the image. And so up to 2010, where we're still using computer vision handcrafted features, and I have done my number of handcrafted features, and I'm still very proud of these handcrafted features, but except that they're not that popular anymore. We had still a classification error of 0.28. That means 30% of the images is wrongly classified, wrongly labeled when we tested it. 2011, it went down to 2%. We got a little bit more sophisticated, had more, better features. But then the big drop of a 10% improvement in classification error came with AlexNet. AlexNet was the first CNN convolutional neural network basically applied to that task. And then, as you can see, there was an improvement over the years. ResNet came in, better architectures, up to 2017 of a factor now of misclassification of only 2%. So went from 30% to 2%, so an improvement on 2 orders of magnitude, which basically means from a somewhat okay system, we went down to an extremely high performing system. By the way, the same thing can also be said about music, right? I'm here just going to talk about images, but when I'm talking here about images also is the same for NLP, natural language processing, of course, and also music classification. So how does one of these learning networks actually functions? Now, this audience, I don't really have to explain it to you. So we need, and this is a toy example of supervised learning. We need large bunches of labeled data, in our case, labeled images. We need neural network libraries. We need GPUs to basically train the model on. And then we're going to get a model where we can feed an image in and hopefully get the right label out. So let me walk through these different components and give you a little bit of my perspective on that. So let's start off with labeled data. It's a conventional wisdom in supervised learning that the more labeled training images or data you have, the better is going to be your model, i.e., it just generalizes better. Because the rule of thumb is if you have not seen a training sample, it's no guarantee that it's actually going to be classified correctly. And so what we use in academia is probably the biggest publicly available labeled training image training set that's called ImageNet. Now, I do emphasize publicly available because there are not that many publicly available data set. Of course, there are a lot of privately held data sets that are probably much larger than ImageNet, but we just don't have access. But I wouldn't be surprised that if Facebook, Google, Amazon, and the Chinese government have much bigger data sets. And that will, of course, also give them better results. So the ImageNet, as you can see, is still very popular, cited for over 25,000 times. And what it is actually consists of is 14 million images that have been hand annotated. It contains more than 20,000 categories, and each category has several hundred images. So each label, if you will, cat and strawberry and whatever, have several hundred images. So the images were actually corrected by harvesting the web. So it's not a database actually of images, it's a database of URLs, just to get around the copyright. And for that, for this harvesting, WordNet was used. And WordNet is a lexical database of semantic relations, including synonyms between words. And that actually more than 200 languages. So the synonyms are grouped into synsets, which is basically, kind of an explanation with short definition and usage examples. So WordNet is basically a combination and an extension of a dictionary and thesaurus. So let's take an example. Female person. And the WordNet definition is a person who belongs to the sex that can have babies. Now, I'm not sure about you, but I find that a relatively limited definition, considering we're here in this conference. And what you're seeing on the right is basically a visualization of 94 randomly selected images from the list of 760 currently functioning URLs for ImageNet's female person synset. That was compiled by one of my former PhD students, Leonard Impet and Al Alexander. Now, if you look at these images, there's one thing that you probably can notice. A, it misses diversity in age, and B, it misses diversity in face color. So not surprisingly, if you train a system like this, you get this kind of disaster, which happened in 2015 to Google, that basically dark faces were classified as gorillas. Now, of course, you can say, okay, 2015, what she's talking about this. I mean, this is kind of like the old, in terms of machine learning times, this is basically, the Stone Ages. But these kind of things are still happening. AI today is used for sometimes just pure nonsense. And I'm showing you now a not quite totally related article that came out in January 2021 in Nature. So this is I'm going to let you look it up where it is from. I'm not going to tell it to you. But this is an article in Nature where somebody basically collected over 1 million faces, fed it into a pre-trained network, VGG Face 2, extracted facial feature, face descriptors, and did some cross-validation logistic regression to figure out that they could predict political orientation in a liberal conservative face pairs of 72%. This is a Nature paper. First of all, I mean, my head exploded, right? First of all, remember 2010 image classification, we had 28% classification error. And I said, oh, this is nothing, this is not usable. How in the world does Nature actually publish a paper where it's 72% correct classification? That's still 28% wrong classification. So this kind of non-thinking application of basically machine learning on visual data just drives me absolutely nuts. And the same thing goes for these papers that claim they can predict sexual orientation, the paper that can actually predict if somebody's going to be a criminal or not, and these are the ones who can actually predict if one should be hired or not. I think these systems based on visual computing are just purely dangerous. Let me talk about the network libraries. Here, I'm not going to say much. Only thing is that the two most popular nowadays is of course PyTorch and TensorFlow. What's to be said about it is actually goes extremely fast. TensorFlow was extremely popular 2-3 years ago. Now it's basically being replaced by PyTorch. So expect the next one to be around the corner. What's interesting though is both belong to the big tech companies. So this is not stuff anymore that comes out of academia. That is stuff that comes out of the big companies. Then let's talk really quickly about GPUs. And this is another one where academia is just lagging behind. So these GPUs, the more processing power you have, the better you can train your model. And the longer you can train your model, and you can make deeper models and you can make wider models. And also cognitive wisdom tells you that deeper and wider models are going to perform better than shallower ones. But, how much can we actually have? And here I'm just going to show you really quickly a post from the Stanford Human-Centered AI Initiative calling for a national research cloud. The reason they're calling for the national research cloud is let me basically enlarge one of the numbers is that it takes, since 2012, 3.4 months to double the amount of compute required for the largest AI training runs. Now, ever since COVID, we do know about exponential growth, and this is exactly it. So we at EPFL have done just a little bit of a survey of how much computing power a typical researcher at Facebook AI has. It's around 250 to 500 GPUs per person, per researcher. Google AI, about 200 per researchers. Apple, several hundred, shared between a few people, et cetera, et cetera. Netflix, Intel, Berkeley, and Stanford. We, in academia, even for Switzerland, even for a rich country, that's just outside of our possibilities. We're trying, we're scrambling behind it, but we will never, none of our PhD students has more than maybe 4 once in a while GPUs. If a deadline comes up, we can blow this up to 40 maybe, but that's about it. So there's orders of magnitude less computing power that we can have in academia. But that's not just the only point I wanted to make, right? There's also the consumption. So these GPUs need power. And this is an interesting article of 2019, and actually it's not an imaging article, but it goes about natural language processing. And here they just actually listed the consumption of CO2 for average kind of life or air travel, New York, San Francisco, 1,984 CO2 pounds emission, human life in a year 11. I'm going to skip the American life. And the car, 126,000 during its lifetime. NLP pipeline parsing is actually relatively, okay, 39. If you start tuning experimentation, you're going to get up there. And then if you actually use a transformer network and combine this with neural architecture search is a technique that automatically finds the best artificial neural network, then you are exploding. You're using 5 times more than in a car average, an average that uses the car that uses that average over a lifetime. And that's just scary. It's also wrong. So while what we can do is a lot of things, but it's not that easy. We're using a lot of power. So what's the take-home message here? Beware of bias in your data set. Oops. Now, the time to train should actually be always reported in all of our academic papers, and hopefully industry will also report it. Okay, sorry. Academic research needs equitable access to computational resources, which is probably a pipe dream, but I put it there anyway. And then, the researchers should prioritize developing efficient models and hardware. And here, let me just give you one quick example. We've actually done this. Here we have, this is an example of Edo Collins, one of my brilliant PhD students, who used some matrix factorization on pre-trained CNNs to do part localizers of an object. So this technique is capable of finding parts of an object, even if the network has never seen these images before. Only thing you need to do is feed about 3, 4, 5 images of the same object to the network. So this is a technique called few-shot learning, and it can actually find parts. So let me show this to you. Here's 5 images of gymnast. If I use just one factor, I basically get the whole body of the gymnast. I can localize this in the images. If I use 2 factors, I can separate limbs and body. 3 factors, I could separate arms and legs and the body. And 4 factors, I can even get the bar. Very similar to the pyramids. Pyramids are not in ImageNet, and very similar to the Taj Mahal. So let me now get to the fakes. Now I see I have to kind of speed up a little bit, so I will do so. Fakes, when you talk about fakes, I'll talk about GANs, generative adversarial networks. Now, GANs were invented by Goodfellows in 2014, basically became popular in 2015, and just totally revolutionized image creation. Now, I'm not going to talk about GAN. Most of you know this. So let me just show you the first results of GANs. This was in 2017. Yes, you know, we could create image faces, but you could see that they probably didn't look that good. But what is absolutely astonishing is the improvement in what you could do. So this is 2018, and this is 2019. 2020, we, like many of the others, also started manipulating the output. So here on the left and on the right, you see, you basically see 2 artificially created faces. And now in the middle, you see basically how you can go from one to the next. But we actually went one step further and started to manipulate parts of the image. And so we have the reference and the target image, and you can see how we, depending on the reference image, can change the eyes on the target image. We can also change the nose, and we can change the mouth. So we are able to now generate artificial images, but not just randomly artificial images. We can actually even edit those images. And it's not just for people. We can also use it for other kind of data sets. Here's the bedroom data set, and what we can change, as in the bed and the pillow and the global kind of changes, doesn't even need to be aligned in the images.
Simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele.
This is actually an example that dates from 2018. So it isn't even that perfect. But just to get the message across, nowadays, these kind of fakes, everybody can do. And again, it's not just the images, it's also the voice. So beware. Now, it's not just that bad, you know. Actually, GANs have also just revolutionized image restoration. And here we're talking about hallucinating not just free images of new videos, but we're starting to hallucinate just missing data. And in denoising, super resolution, in-painting colorization, we have just done tremendous kind of work. And that's where the good part of actually this GAN comes in, and it helps in just the network. So in this case, this is an example of the lab. We used the GANs to actually estimate missing kernels of camera to have a real world super resolution algorithm. And here, I don't know if this is seeable, but you can actually see on the right-hand side our method, and it is actually sharper. So now I think I have 1 minute left to talk about fiction, so I'm going to make it very fast. And to be honest, this is just a plug. I'm not going to talk about fiction or visual computing because I wouldn't even know what to dream at. It's just going so quickly. So I'm only going to talk about the fiction, and in this case, our startup, which deals with fiction, and that is Largo. And basically, what Largo is an AI machine learning-based tool to help film production. And, you know, you have a lot of important decisions to make if you make a film. You know, who the actor is, which script to choose, who's the producer, who's the director, where are you going to release it first, etc., etc. So in general, these kind of decisions are done by gut feeling, except, of course, by Netflix and Amazon, who've basically optimized based on machine learning this a long, long time ago. But of course, these algorithms, again, are not publicly available. And so we are basically trying to build Netflix's and Amazon's data-driven movie making and not just the gut feeling. So what our innovation is, we're basically using machine learning to do, get the genre of the script and the film and the description, and we can then do casting proposition and working forecast. I'm going to skip all this so we can finish this. And thank you very much for your attention.
Yeah, thank you, Sabine, for a very exciting talk. I see a lot of discussions, and a lot of questions that pop up. So the first question, what are some practical approaches to preventing bias towards gender, race, etc. in CNNs?
Well, it's data. And one of the things, and this is one of the absolute biggest thing, and I think the previous speaker of the Swiss Data Science Centers, they can actually talk about this, is data curation is always underestimated. Your trained network is only as good as the data you feed it, right? I'm not talking about transfer learning and unsupervised learning, whose performance is actually worse than supervised learning. But you need to do a good data curation, and this is why I'm mentioning bias. And I mentioned bias in the beginning. Everybody has bias, maybe an unconscious bias, but you cannot just suck up images of the internet and think this is going to be a real data set. You need to truly actually look at the data to learn it and balance the number of samples. And there's a lot of work that needs to be done for this.
Yeah, okay, thank you. And another question, are you aware of research in AI that aims at being more energy efficient? So
yes, basically, yes. So there's a lot of, the examples, by the way, I showed you, even with the GANs, we also use pre-trained GANs. So there's a lot of research being done on transfer learning, for example. So you can actually take a pre-trained model, transferring it to another image domain. In the idea of, this idea of few shot learning. So you have a pre-trained network, you just need a few more examples of new data to actually enlarge the model. Then one shot, zero shot learning goes in the same direction. So there's a lot of work being done there. The only thing that I need to tell you is that while that's going on, there's a huge new area coming up, and that's adversarial learning, i.e. when you have perturbation either in the data signal or in the network. And that again takes even more processing power to actually make robust model in this. So at the end, I think we're going to, the more we can open that black box and make it a white box, the more we can probably truly target, the problems we're trying to solve and make it also more energy efficient.
Yeah.
And then, by the way, let me also say this. And then, in parallel, there's of course a lot of work going on in computer science in the data centers, how to make the data centers more efficient. But that's not my specialty.
So I have another question. So I have so many of them. To connect to the previous talk, how fast do you think we can build hardware that will enable us to still do research in computer vision at the same space without having a large carbon footprint?
Not fast enough. Because exactly, at a certain point, the basic hardware architecture is still somewhat the same, right? I mean, the Moore's law, right? I mean, the processing power doubling, it's plateauing. I have not seen, but then again, I remind you that's not my specialty, but I have not seen nor heard of, orders of magnitude faster chips that are going to come out. What I've seen is that, some ISIC processors that can do one thing faster, but TPs are getting more powerful, but they're not necessarily getting more efficient. And by the way, putting these data centers then in Antarctica is not a solution either, right?
Right.
Mm-hmm.
From your perspective, which advantage do you see from a machine learning researcher to do research in academia with industry?
In academia, when you're in academia, you can say bad things about industry, like I just did. No, I'm just teasing. No, I mean, the thing is, it's a different kind of career, right? I also think what you can handle, if you stay in academia, you can handle problems that are not handled in industry, right? I mean, we heard about the Swiss Data Science Center, right, which actually helps, climate change. You can really choose the topics you want to apply your research at, and you can do well. In industry, you have the freedom, you have the power, but at the end, you're going to research something that, except if you're extremely lucky, right? If you, what the company wants you to do.
Right.
Yeah.
Yeah. Yeah, I think we have to stop with questions, but Sabine, she will have a Q&A session as a mentor.
Yeah.
At 1:45, so for 15 minutes. So if you have more questions, because I still have like a lot of questions, so you can ask her there. So I would like to thank you, Sabine, one more time to speak in our conference. Thank you very much.
Thank you very much for the invitation.
Yeah, thank you.